was cool when he always just quotes his wife. Is like, oh, by the way, and then turn around to the suspect and say, my wife wants me to ask you about the recipe of the apple pie, or something that's completely irrelevant to the case, just to throw off the other guy, right? Anyway, I think most of you do not know Columbo. No?
They're all Quincy fans.
All right, so what we'll do is we'll do a sorting algorithm in C first, and then we'll do it in assembly. So I'm going to go through the entire process of starting with structured C code, make sure the structured C code is working first, and then do it step by step and flatten the C code into something that is completely assembly language friendly. And then we'll start to do the conversion into assembly language. Okay, so which is kind of a recommended way to start on this kind of homework assignment. If you feel comfortable starting right off with assembly code, that's fine with me too. All right, so we'll do a sorting algorithm, and I'm just going to put everything into the main subroutine. We'll start with a character array. Okay, so and we'll just call this string, and it is an array of characters, and this is how I'm going to initialize it. So we just make a bunch of mumbo jumbo. Okay, doesn't matter what is here, because the objective is to sort the entire thing. So I want to sort all the characters within the string, and I'll just use bubble sort, because bubble sort in terms of the logic is easy to specify. In terms of runtime complexity or how much time it takes to execute, it's not efficient at all. But in this case, I just want the simpler logic. With bubble sort, there are a few things we have to keep track of. There are a few pointers we have to keep track of. So I'm going to declare a few pointers for that. So we'll have PTR as a character pointer, and I think that may be all that I need, because it's always comparing to the neighboring one. So this is probably going to be okay. And I'll also need an extra character for swapping purposes. I'll just call this T, because it's a temporary variable for swapping purposes. All right, so this is actually going to be quite a bit more complex than your homework assignment, so the approach would still be applicable. It's just that this is going to be a little bit more complex than your homework assignment. All right, so what we'll do is we'll do this one step at a time. So I will say, while PTR is still pointing to something that is non-null, okay, do the following. In fact, we want to say if PTR plus 1 is pointing to something that is non-null, you do the following. Or, we can also say, if PTR itself is pointing to non-null and one step ahead of it is also pointing to non-null, we'll do the following. Just in case the string itself is empty to begin with, because otherwise it won't catch it. If the string itself is already a null string, this will catch both cases. All right. So within the loop here, we just compare whatever pointer PTR points to whatever PTR plus 1 points to. If they are out of order, we exchange it, and we increment the pointer, and then we move on to the next iteration. So that's the basic step of the inner loop of bubble sort. So we'll just do the conditional statement here, and basically just compare whatever PTR points to, and say if it is greater than whatever PTR plus 1 points to, then they are out of order. If they are out of order, we do the usual swap sequence, which is to use a temporary variable T to store one of them. Doesn't matter which one you start with. I'll start with whatever PTR points to, and then change whatever PTR points to the other one. In this case, it is whatever PTR plus 1 points to, and then we'll change whatever PTR plus 1 points to T, which was the original value in whatever PTR points to. So that's a very typical swap logic. Is that part still okay? The swap logic, okay? And at the end, we will have to remember to move PTR forward by 1 byte, so that we are moving on to the next character in the string. All right, so the way it is right now is not going to work. The compiler will actually complain about this if I turn on warn all, it will say the PTR is not initialized, before we start to use it the first time. But since I'm catching it myself, I'll just go ahead and initialize PTR to a string. I'm not sure whether I can use string because I think lowercase is fine, uppercase is already a class name, but I'll just be cautious and just call it str. All right. So at this time, I'm just gonna double check, make sure it is recording with the voice. Yep, it is. All right, so at this time, we can test the inner loop of sort first, just to make sure that this part is working. We only have to go through like 1 or 2 iterations to double check that it's working. Okay. So let's go ahead and do that. G++ -1 all -pedantic -g-o sort.cpp. And it complains about return with no value in function. Oh, okay, I forgot to specify return value because main is supposed to return an integer, and I just said return with no value. Okay, let's do it again. This time is good. GDB sort, and we'll put a breakpoint on line 18. Print str. Oops, I have to put a breakpoint on line 7 first. Run the program. Print str, which is the original string, and then continue execution until it stops. Oops, it's an infinite loop. It's not stopping. I forgot to do one thing. All right. So print PTR, and it is still the same. So I forgot to update. It's not ending. Okay, let's debug it. Oh, put the increment in the conditional statement. So if we don't get into the conditional statement, it doesn't get incremented. Then it will keep in the same loop over and over again. Okay, that's it. Okay, so let's do it again. Do another GDB. Put a breakpoint on line 7. Put another one on line 18. Run the program. Print string from the beginning. Continue execution. Print string again at the end. So let's see whether it is working or not. Because with bubble sort, with the code that I have written, it will push the largest character all the way to the left-hand side. The rest is maybe in order, maybe slightly out of order. It depends on what the original string is. So out of all the characters in the original string, which one has the largest ASCII code? A lowercase s, and it is now all the way to the right-hand side. So this part is working now. Okay. So now we have to. Do you guys want to just work with this? Because this is already kind of good enough, for the illustration, for illustration purposes. It's not the complete bubble sort algorithm, but it's good enough for the illustration of your homework. Is that good? Because it has all the comparisons and stuff like that. Okay, so let's go ahead and do this one. All right, so let's quit this. And we'll try to convert it into assembly. But before we convert it into assembly, remember what I said, we'll have to flatten this first, okay? So this one is actually good enough for flattening because it has got a conditional statement inside a while loop, and we have conjunction and all kinds of stuff that is kind of more complex than your homework assignment. We'll do one thing at a time. So I will focus on the conditional statement first. The way to convert this into a flat structure is to get rid of the conditional statement so it becomes just a conditional part and then go to the label. So what we'll do is we're changing the direction of the comparison and then say, oh, if this is the case, we go to the label and if. And then we define label and if over here. And because now it is flat, I no longer need to have open and close curly braces. I don't need a block statement anymore, because the only statement for the conditional part is a go-to statement. It goes to and if. So that means t gets whatever pointer points to and so on. That is no longer necessary to be a single statement. It doesn't have to be a block statement anymore. So I have just flattened the conditional statement itself. Any questions about this step? If there are no questions, I'm going to move on. I'm fairly sure this is actually, other than using a colon instead of a semicolon, I'm pretty sure I did not change the meaning of the code. So I'm going to go forward and flatten the loop itself also, okay, without checking it first. So when you flatten the loop, it's kind of the same thing. You look for the opposite of the condition in a while loop, and then you say when the opposite of this, or when the negation of this is true, you get out of the loop. So instead of looking for a condition to stay in the loop, you are looking for a condition to get out of the loop. So one way to do this is simply to say if it is not this condition, go to end while. And end while obviously marks the end of the while loop, so it has to be here. But we also have to remember now, because it is a loop, it has to go back to the beginning of the loop at the beginning of at the end of each iteration. So I need a begin loop defined here, and put a unconditional go to here to go to the beginning of the entire loop. So that will flatten the loop itself, which means the open and close curly braces for the loop are no longer needed because nothing is really structured at this point. Are there any questions about the flattening of the code? Okay. So at this point, it's probably a good time to test it again, just to make sure that I did not really change the logic of the program itself. So I'm going to recompile the program and re-GDB the whole thing. Put a breakpoint on line 7, put another one on line 18, run the program, print str before we do anything, continue execution, print str again, and the program is still behaving correctly. Okay, it's still doing its job. So that's good. That's encouraging. So that at this point I can go back and now try to flatten the conditions, not the control structure, because the control structure is all done already. When you are doing this, you are strongly encouraged to use a revision control type of mechanism. It can be as simple as just resaving the file in a different name, okay, so that you remember all the versions of the code before you make all the changes. You can use CVS, you can use RCS, you can use get, sign up for a free account at GitHub, but do something to perform revision control, because employers need employees who know how to use all those tools. Any questions at this point? No questions? All right. So at this time, I have this kind of more or less complex expression here, which has a negation on the outside, and then inside we have basically two implicit comparison. Okay. So to make this really clear that this is a implicit comparison, that's basically the same thing as this, okay? Because when I just say asterisk PTR, I'm actually asking, is it pointing to something that is not null? So this is the same thing over here, and I have trouble matching the parentheses. Nope. Okay, that will be good. Okay, so that really is what is meant here. But the other way to convert this is to use De Morgan's law. How many people know what is De Morgan's law? De Morgan's law is a transformation that can take the negation of a conjunction into a disjunction with individual negations. So I'm going to write it out, and if you guys want to use it in your own program, you can go ahead. It's just a really useful technique for programming in general. So I'll go ahead and just talk a little bit about De Morgan's law. It's called De Morgan's law. And the way it works is like this, okay? It basically states that the negation of A and B, A itself can be a big, huge expression, and B itself can be a big, huge expression. But the point is, A is Boolean and B is Boolean. This is really the same thing as saying not A or not B. Is that making any sense? Now, if it doesn't make sense to you, it's still okay, because what you can do is you can use a truth table to prove that the two expressions are equivalent. They're exactly the same. Now, because A is Boolean, it can either be true or false. B is also Boolean. So while A is true, B can be true or false. While A is false, B can be true or false, because these two Boolean quote-unquote variables are independent. So now we can go ahead and evaluate when A is true, B is true, A and B is true, not true is false. And then over here we have not A is false, not B is false, false or false is also false. On the second row we have A being true, B being false. True and false is false, not false is true. On this side we have not A being false or not B. Not B is true because B itself is false, so together it is also true. So this one is symmetric, so it's going to be true and true also. And then on the last row, A is false, B is false, A and B is false, not false is true. And over here, A is false, not A is true. B is false, not B is true. True or true is also true. So when you look at each row, you can see that the result of the first expression, which is not A and B in parentheses, has exactly the same value as not A or not B. And that is proof that these two expressions are truly equivalent. Okay. This is a technique that applies to Boolean algebra, but it doesn't really apply to algebra of other kinds, because you cannot enumerate all the possible values for integers, right? But for Booleans, you can, and that's why it's a very useful technique for proving one expression is equivalent to the other expression. So without proving, I can now tell you that this can also be expressed as not A and not B, which is kind of it makes sense in a certain way, but but that is also true. And this is De Morgan's law. It allows you to go from one form to another form. Are there any questions about this? Okay, wait, hold on a second here. How does this apply to what we are talking about? What are we talking about here? We have code that looks like this, where the negation is on the outside, and then we have a conjunction in the inside. So now we can break it up. Okay? So now we can break it up into two expressions connected by a disjunction, but the negation goes into the sub-expression. We're basically just applying De Morgan's law in this particular form. Is that okay? Because what we have right now in the source code is this. And in order to make it easier to deal with, we want to convert it into this form. So that's what we're going to do. So that means, I will change this to a OR, logical OR, take the outside negation away, put it into the inside, like that. Okay? Now, if you're kind of doubtful whether this is going to be the same thing or not, all you have to do is to rerun the C program and kind of use it to convince yourself that it is really doing the same thing. But now we have something that is completely redundant, because if you look at this portion here, it is not the case that PTR points to something that is not 0. Isn't that the same thing as saying PTR points to a 0? Yeah. Okay, well, that's a really easy way to simplify this expression without using any additional logic, right? And the same thing applies here. The negation is on the outside, and then inside we have a not equal to. So we can do the double negation thing and say, oh, okay, I guess we're just looking for an equality to a null. Okay. Yep. So once we have it in this form, now we have to get rid of the disjunction. To get rid of a disjunction is pretty easy, because you just have to say, oh, if the first condition is true, we go to and while. Oh, if that is not the case, we check the second one. If it is true, we also go to and while. So to convert this part into, to get rid of the OR, you're basically just saying, oh, in the first one, we check for only the first condition. If that is true, we go to and while right away. If the first condition is not true, then we'll go ahead and evaluate the second condition and see whether the second condition is true, because if the second condition is true when the first one is false, we also want to go to and while. So that's how you convert, get rid of the disjunction, the bar, in this case. So at this point, I have pretty much all of it expressed, in in a completely flattened manner. Flattened means the condition itself involves a single comparison. Okay, they are all single comparison at this point, and the conditional branches will be in the form of using the result of a comparison to determine whether we should branch to a particular label or not. And we only have that kind of construct at this point, which means we're pretty much ready to convert it into assembly code. Are we still doing okay? Yep, go ahead.
For the if, the one that was said the while loop, why did you switch the greater than that wasn't listed?
Because we are looking for the negation of the original condition so that we branch around it. It's trying to determine when can we skip around the then branch instead of saying when do we get into the then branch. So that's why it's negated first, but the negation of greater than is just less than or equal to. So instead of using the other way, which is introducing additional go-tos and whatnot, this is just easier because it remains as a single comparison. I just flip the direction.
But it's still the same thing, right? It's still the same thing, right?
This logic still means the same thing as the original code, yes. All right, so, yep, go ahead.
Did I see De Morgan's law one more time?
Sure, absolutely.
It's almost as if you distribute the not into the parentheses on the left side.
Right, but you have to change the operator.
Yeah.
In the process of distributing the negation, you're changing the operator so that and becomes or becomes and. Yep. But it's a very useful technique, because if you start with something like this, you can save like an operator by changing it into this form. So it has a lot of interesting applications. In electrical engineering, there are devices where you only have a certain types of gate, like a NOR gate or a NAND gate. So if your original expression uses the other operator, this is how you can flip it and use the operator or the type of gate that is actually supported by the hardware device. So it has a lot of applications, not just programming, but in electrical engineering in terms of gates and the design of electronic components. It also has applications. All right. Any other questions before? Okay, if there are no questions, I'll do one last check with the C code, the flattened C code, just to make sure that I start with a C code that is actually still working correctly, that does what the original code is doing. So we'll once again do a G++, GDB, put a breakpoint on line 7, put another one on line 19 in this case. Run the program, print string, continue execution, print string again. And the program is still doing what it is supposed to, which is good. Okay, that's what it's supposed to. That's a good sign. All right. So what you should do with your homework assignment, especially if you don't feel comfortable programming in assembly like right away, is to do it like this first. Okay, because C programs are fairly easy to debug, especially if you use code blocks or some of the IDEs. You can set up breakpoints, examine variables and stuff like that. It just makes debugging a whole lot easier. But once you have the completely flattened form of the C program, then you are pretty much ready to convert it into assembly, because you can preserve the same label names. Okay, if it works in the C code, it will work in your assembly code. If the logic is right, it will still be right. The only part that you're converting is how do we move something and how do we compare something. Yes, there was a question. I thought I heard a voice. Could be just inside here, Okay. Somebody was talking to me telepathically. Okay, so now I'm going to copy my C program into a assembly source code. And in the assembly source code, I will cut off all the stuff that I don't really need. In fact, I'll just add comments to everything first. Okay, so I have the entire original C program here, and then I'll start to convert it into assembly code. So with this, the data portion has to deal with all of the variables. Okay. So with this, I'm going to have to say, okay, what is the equivalence of declaring a initialized string in assembly code? Well, it's kind of like this. Okay, so string colon, which means I'm now defining a string as a label, str as a label. And this time I have to use ASCII, ask keys, which means I'm using a string, but I also want a no terminator at the end of the entire string. If you use ask key, changing the z to an I, it simply means that is exactly what it is. But if you change the I to a z, it means we also have a no terminator, which is the C standard of how to end a string. Okay, so we have that. Yep.
Are there any other variations on that for ASCII specifically?
No, just ASCII, with two I's and ASCII's with IZ at the end. And this is the one that I want because I want to preserve the actual original logic of the program. Now, as far as PTR and T are concerned, you can use these. You can use like a dot int for the PTR and a dot byte for the T. It depends on whether we have enough registers to play with. Okay, so for the time being, I'm going to say, well, let's not make variables out of these guys first. Okay, and so we have to switch back to the code section, which is called .text, and then we say .global _ start to basically export the label to start the entire program. And then we say _start. This is the entry point of the entire program. This one is fairly simple. I want the pointer to start from the very beginning of the entire string. The pointer means it's meant to be dereferenced, okay? Because otherwise I would not need a pointer to begin with. So for anything that is potentially going to be dereferenced, if you can use just the registers, that would be the easiest way to do it. Okay, just use all the registers and you're done. So in this case, I'm not having a lot of variables, so I'm going to say, okay, let's just allocate one of the registers to PTR. So PTR is no longer quote-unquote a variable, it is now a register, because we can do indirect operands with registers. So to do that, I can now say, in comments, I'm going to say EAX is PTR. Just to remind myself from here on, I will consider EAX as the pointer in the original code. So to initialize EAX to point to the beginning of the string, is really just copying the label using the immediate operand to EAX. Okay, I'm not copying the content at the label. I'm just copying the value of the label itself, because the label itself is the address of the first byte of the .ASCII directive. Is that okay? Okay, so don't forget the $, because without the $, it's completely different. It becomes a direct operand. Okay, next line, defining the label begin while. This one I can just keep it, because the way we define a label in assembly is the same thing as how we define a label in C and C++. So that part is okay. This line here gets a little bit tricky. Okay, how do we compare 0 to wherever PTR points to? Well, this one is not tricky. The next one is a little bit more tricky, because in this case, there's only one memory operand. 0 itself is a constant. It is not a memory operand, because we can use $0, immediate 0, for the right-hand side of the equality check. So we only have dereference PTR as our memory operand. And we can use, which addressing mode should we use in this case?
Indirect.
Indirect, okay? Indirect is the one that can do the dereference and it accesses memory locations. So we have a compare instruction here. The immediate operand has to be the first one, cannot be the second one. So that makes the indirect operand the second operand. So this instruction will actually assemble. But if you specify it like this, you are now telling the assembler and say, hey, assembler, you decide for me how wide of an item I'm comparing. Guess what? The assembler defaults to long, which is inappropriate in this case. Because what am I really comparing? What is the type that PTR is pointing to?
The first character.
A character, right? It's the char type. And the character is only a byte, okay? So if you're comparing a long instead of a byte here, then it may not even terminate. because the null terminator at the end of a string is only guaranteed to be a character of 0. There's no guarantee that the 3 other bytes behind it are also zeros. So if you compare long, you may never catch the null terminator if the null terminator is in fact just one single character of null character. Do you see what I'm saying? Okay. So that's why I personally will never leave it up to the compiler or the assembler in this case to determine the width of a comparison. I always specify let's compare byte in this case. Now in some cases, if you're comparing immediate to just the register EAX, yes, it is implicit that the comparison is in 32-bit anyway. Okay. In fact, if you try to specify compare byte $0 to just EAX without the parentheses, the assembler will bark at you and say, no, can't do this, okay? Because you specify a 32-bit register and now you're trying to compare byte, it doesn't work. But in this case, because it is indirect, the register itself does not indicate the width of the comparison because we're comparing to what the register is pointing to, not the register itself, okay? So in this case, you have to be very careful and actually specify the width manually. And then after this, we have a JC instruction because we're just looking for equality in this case to the label end while. Okay, so now we're moving on to this one. This one is a little bit more kind of complex because we have to compare not to the byte that PTR points to, but the one that is 1 byte beyond that. There is a very easy way to do it if I have talked about the based addressing mode. So I will give you the solution without using base addressing mode first, and then I'll go back and talk about the base addressing mode, okay, which is a very handy way of doing things, but it's also a very CISC-ish way of doing things, which I don't like. Okay, so without knowing what is a based addressing mode, then we'll have to say, wow, the only thing we can do this is to actually add one to the register EAX or use another register to calculate PTR plus 1 and then do the comparison that way. So let's do it that way first, and then we'll go back and talk about some other solutions. So let's just say that we go for the kind of like a scenic route, okay, but it works. So we'll copy EAX, which is PTR itself, to register, let's say EBX. Okay, I'm just picking the next available register. And we say, okay, now we need to add one to EBX because we are supposed to compare to not where PTR points to, but where PTR plus 1 points to. So this is the plus 1 part of the expression. Then we can use the same compare byte instruction, except we are now using EBX as my indirect register and not EAX, because EAX is still PTR, EBX is PTR plus 1. Is that okay? All right. So after the comparison, we also say, oh, if it is in fact 0, the null character also go to end while. Okay. So this is one solution. Okay, it's not a bad solution. It works, and that's all that I care in this class. I'm not looking for the most optimal way of doing things. I'm just making sure that you guys know one way of doing something. So this works. It's good. We'll move on. So by the time we get to this conditional branch here, we already know the PTR is in EAX. We already know the PTR plus 1 is in EBX. Is that okay? Because I wouldn't be able to get here unless the comparison of the previous one was already successful, which also means I have to be PTR must be in EAX already, and PTR plus 1 must be in EBX already. So I can make use of that fact and not have to reinitialize EBX. It's not wrong to reinitialize EBX, it's just that it's not necessary in this case. Okay, so knowing that, we have a comparison, so it would be nice if we can do this, okay? It would be nice if we can just say, oh, compare byte. In this case, I have to flip the direction of all that stuff. So we're comparing what EBX points to whatever EAX points to. And we preserve the comparison operator here. Since it is less than or equal to, it is basically saying not greater than, right? So we have to pick NA or NG in this case because it's not greater than. ASCII code is basically unsigned, so I'm just going to use JNA in this case. JNG would work just fine because everything that we can type would fall into 0 to 127. So whether the comparison or whether the conditional branch is signed or not really doesn't make a difference. Yep.
Isn't the 2 indirects going to cause a problem?
It will. Remember what I said? It would be nice if I can do this.
Okay.
So we're going to fix it later. We'll fix this, but not right now. Okay. So we're just going to do it this way and move on, and let the compiler complain about it later on. Okay. So we'll leave it up to the compiler to complain about it. All right. So now we have T and PTR. We have used EAX for 1 for PTR. We have used EBX for PTR plus 1. Hey, we still got 2 more registers. Okay, so I don't want to allocate from memory unless I have to. So in this case, I don't have to. I can just use ECX to represent T in this case. So I'm going to use a move byte, and I'm moving whatever PTR points to CL or CH. Pick one. So the first operand is going to be indirect EAX, and the second operand can be CH, CL, DH, DL. Just pick one of those. Okay, I'm just picking CL. Okay. Any questions about this part? Yep.
Not really a question, but don't you need to specify where JNA is going to jump?
Where you're right. There we go. Thank you. Now, as much as it sounds really bad because it sounds like I'm just finding an excuse, these are minor problems. Anything the assembler can catch, and it is just a straight copy from the C code to assembly code, those are easy problems to fix. The hard problems to fix are the ones that the assembler cannot catch. Okay. For instance, not remembering to use the parentheses in this case. Well, that one the assembler will catch too, because then EBX is not a byte. So let me pick one that is not easy to find. All of these are fairly easy to find except for this one. Missing that $sign up here. It is syntactically still correct, because without a $sign, it becomes a direct operand, and the direct operand is different, completely different from an immediate operand. But syntactically, it is still okay. But then your program will crash because you're not actually moving an address into EAX. So the first time you use EAX as an address, it's going to crash. But the problem is not because of the compare byte instruction, it's because how EAX is initialized. Okay, so we are now back here. All right, so once again, we have 2 memory operand. I'm going to pretend that it will work. It's not going to work, but I'll just pretend. So we'll say, oh, it'll be nice if we can just move whatever byte EBX points to whatever byte EAX points to. And then the last one is move byte. At this time we have register CL being our T. We'll copy that to whatever EBX points to, because EBX is PTR plus 1. So it'll be nice if we can do that. And if it's the same, because we're just defining a label. Adding 1 to PTR is just add long $1 to the register that is our pointer, which is EAX. And go to begin while is unconditional branch jump to the same label name, begin while. Define end while here. We don't actually have a return 0 at the end of our program. We have this kind of weird sequence of instructions, moving 1 into EAX, and then moving a 0, which is the exit code, into EBX, and do a interrupt. Basically, it's a software interrupt. All right, so we have this kind of program sort of written, but it's not going to assemble because I said, you can only have up to 1 memory operand. So this is not going to assemble. But we want to see the error message first, just so that we know what type of error message we should get when we try to do something like this. And it says too many memory references for the compare instruction on line 25, and the same thing on line 30 for the move instruction. So yeah, we knew about this problem. I told you guys that it would cause this problem. So now it's time to go in and try to fix that problem. All right. So the first problem is here. I cannot compare 2 memory operands. Well, I can use an 8-bit register to store the byte pointed to by one of the registers, and then use that to compare, use it in the compare instruction. So I can just do something like that. Which one I pick doesn't really matter. Let's just pick whatever EBX points to. I put it into CL. Okay. So we have a move byte instruction here. Whatever EBX points to, we put it into CL. So in the next instruction, we just have to compare register CL to whatever EAX points to. That's the trick to get around it. Okay. And the same thing for the move instruction. So with the move instruction here, now this one I have to be more careful because CL is already in use for something because it's T down here. So I have to remember not to use CL. I can use CH, which is a different 8-bit of the register ECX. So that would still be usable. So I have to say move B in this case, EBX to, let's say, register CH. And then in the next instruction, CH will take the place of indirect EBX because that's the same thing. And now I'm not using two memory operands anymore. So are there any questions about how to fix the problem when you need to access two memory locations in the same instruction? Yep.
CH and CL write differently? They don't overwrite, CH doesn't overwrite CL?
That is correct, because CL is bit 0 to 7 of ECX. CH is bit 8 to bit 15
So no
of that
pattern.
register, so they do not overlap.
Okay.
It'd be CW, wouldn't it? The one that would overlap would be CW.
CX, yeah.
Oh.
Yeah, CX refers to bit 0 to bit 15 of ECX. So yeah, that basically becomes the concatenation of CL and CH, basically. Are there any questions? Yep, go ahead.
So we're using CL right there, and then you're using it for T later on. Would that
Right.
like,
No, that won't be a problem because the use of CL as T is limited only to those 3 lines of code, and the first use of CL is outside of that context.
Is it because it's going inside of the empty statement?
Okay, let me put it in another way. Okay, let's turn on the line numbers first. So from line 29 to line 34, that is quote unquote the scope of CL being T. But other than outside of this scope, CL can do whatever it wants to, okay? Because it doesn't need to retain the value of T after it gets out of this scope or before it enters this scope. So that's why outside of the context of line 29 to line 34, I can use CL for other stuff. I can use the entire ECX for some other stuff if other parts of the register ECX is not in use. That's a good question, but yeah, that's the answer to that. Right? Yep.
But earlier in the class, you mentioned before that you don't have access to the bits 16 through 32.
Yeah.
You can only use CL and CH.
Correct.
Wouldn't it be much more useful to be able to use all the different sort of subdivisions of that register?
That would be correct, but you have to tell Intel that.
Oh.
The instruction set only allows you to access out of ECX, which is a 32-bit register. You can designate bit 0 to 7 as CL, bit 8 to 15 as CH, bit 0 to 15 as CX, and then the entire thing from bit 0 to 31, not 32, 0 to 31 as ECX. Yep.
So after line 34, CL will still have the value of T until you change it, correct?
That is correct.
And if we go back into the loop, it's changed on line 25 to be something else.
That is correct. Yep. In fact, there are ways to make this more efficient, but there's no need. I mean, the way it is fine. Yep.
I also noticed like there's you do an indirect, like you do an indirect with the parentheses, and then you put like number line in front.
Yes, that is called the base addressing mode. Remember what I said? I said there's a way to make this easier, but I'm not gonna introduce another addressing mode at this point. I'm just gonna do it the way I'm gonna do it the risky way, RISCY, risky, not KY. Because in the end, I think cisp is going to persist more so than, RISC is going to persist more so than CISC. There will be more and more devices using RISC processors instead of CISC processors. We are probably be looking at the last generation of really CISC type processors for the next maybe until Microsoft gives up. When Microsoft gives up on supporting the Intel i386 instruction set, that will be the end of it. There will be no more reason to use CISC processors anymore. So after that, it'll all be RISC type processors.
Is it like a VHS beta kind of thing?
It's not exactly like that because there are benefits, profits, profitability issues with CISC versus RISC, as opposed to beta versus VHS, which is a quality issue. Right. But in the case of CISC versus RISC, RISC has a few advantages over CISC. One is energy to processing power ratio. For the same amount of energy, let's say 1 joules, okay, with a bunch of RISC processors, because one is kind of weak, you need a whole bunch, but together on a per energy unit basis, they can perform more computations than a CISC architecture.
Which one's more efficient to create via wafers?
It's also RISC because each RISC chip, processor chip, is smaller. So given you have X number of defects on the same wafer, if you have smaller chips, that your yield is still higher than a bigger chip, because with a bigger chip, if a defect lands on anywhere within the chip, that particular chip is gone. But with a smaller die, that means the probability of having one landing on one single chip is lower. You will still have the same number of defects on the wafer, but the yield goes up regardless. And the other way to think of this is, what if we have one super huge chip that uses up the entire wafer, right? Then if on average you have let's say 3 defects per wafer, then you will never be able to manufacture that particular chip, because there's always one defect somewhere to make the entire thing useless. Is that making any sense? Yep. So that's the one big argument about why we should use RISC architectures instead of CISC architectures. The whole thing about the CISC architecture is completely historical. It's just because Windows is compiled for the CISC architecture. There's no other particular reason for that. All right. Yep.
CISC architecture is Intel, right?
It depends on how you look at it. With a CISC architecture, there will be different ways of doing the same thing, or many different ways of doing the same thing, as opposed to a RISC architecture where there's definitely one clear, easy solution to do something. It might involve multiple steps, but those steps would be fairly easy to evaluate which one is better. So as far as a compiler is concerned, a CISC architecture makes it harder for optimization, because now you have all of these alternative ways of doing the same thing, and the compiler has to figure out which way is faster. And which way is faster does not depend only on the instruction that is currently in question. It also depends on how the pipeline is set up, what other registers and ALUs are doing at the time. Because now you have a single core that has multiple ALUs. So a compiler can take that into consideration and schedule instructions to try to maximize the use of the ALUs in parallel. So with all of these things happening, a CISC architecture is much harder to optimize, because now you have all of these factors and all of these different ways of doing the same thing, whereas a RISC architecture is simple by design. The hardware is simple, so in terms of optimization, it's also simpler. Any other questions? Those are all very good questions, by the way. And at a 4-year university, sometimes they only bring up those topics in their kind of like a upper division computer architecture class. Yeah, they do.
Well, I'm just thinking of how lame that is that they have to wait so long to educate their students about that. Unlike us, privileged kids.
G-stabs, sort.o, sort.s. Good. I didn't make a syntax error. LD-O sort O GDB sort. All right. Oh, it complains about something. Nope, there's no complaint. That's good. All right, so we'll put a breakpoint on line 14, which is at the beginning of this loop, this program, and we'll keep going and put a breakpoint on line 43. Print string is not going to work. Okay, so let's think about what's going to happen when we execute this command in GDB. Print string. Now remember two things. One is assembly language is typeless. Okay, so str is nothing more than just a label and say, oh, by the way, the address of this byte is also known as str. That's what str is. Okay. Then second thing is GDB wants to be smart. Okay, so when you say print str, GDB looks up the symbol table and say, okay, what is the type of str? And obviously it cannot find anything because labels in assembly language has no particular type. So GDB is going to say, okay, let me give it a default type, and the default type is an integer. Okay, so when you print str, it's going to print the content at the address str, but it will interpret 4 bytes at that location as an integer. So this is going to be, if I print it in hexadecimal, that will basically spell out the ASCII code of the first 4 characters of the string. The least significant byte being the first byte, the first character, and so on. So let's see whether that really is the case or not. Okay, so we have 6F, 6.9, 6.1, and 7.3, and the string was what? I cannot remember. The string was OIAS. Okay, so this is that O? 6.1 is, that doesn't sound right to me. 6F, because 6.1 is a lowercase a. Okay, this is definitely a. I know that for sure. This has to be O. This has to be I. Oh no, it is O. Okay, let's count. I don't know my alphabet well enough. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Yep, it is. Okay. So it is O. 6F is the ASCII code of lowercase o in hexadecimal. So this is corresponding to this byte here. 6.9 is corresponding to I because it is A, B, C, D, E, F, G, H, I. So it's 9. And then we have 6.1 being lowercase a. It is just the first one of the ASCII code. And then 7.3 is basically 16 plus 3, which is 19. So so that basically is lowercase s right here. So just as I said, it will interpret the first 4 characters of the string as an integer, and that's why the bytes are ordered this way. Are we still doing okay so far with this code? Okay. So we'll go ahead and run the program until we get to the second breakpoint. We put up a second breakpoint already, so we'll just go ahead and run the program. We are now at the first breakpoint. We'll continue execution, so it gets to the second breakpoint, and now we want to look at the string again. So what you can do is to cast it. Okay, so you can basically cast and say, make str the address of str, actually in this case, a character pointer. Then it will print it out as if it is just a string, but you have to cast it first, otherwise it won't know what kind of stuff we're dealing with here. So in this case, it is the same result as in the C code. So I just finished translating the program from C, structured C code into assembly code. Are there any questions about this process? Questions? Okay. I'm going to pass the row sheet, and I'm adding a new column because I forgot to bring the latest one. When I remember to bring the latest one, I forget to pass it around the class. So that's that. All right. Any questions about this? the process itself, the addressing mode that we talked about, how to flatten the original C program. The VI commands that I use to insert all the pound signs.
Well, how did you do that? I know I'm gonna be stuck inserting them on my hand if I don't.
Well, you probably don't need to learn it like right away. The way to do it is to do a type of colon first, so that will put you into the command line mode in VI. Dot is basically the first line, so you can specify just one as the first line. Comma separates the first line of a range from the end of the range. Dollar sign by itself specifies the end, the last line of the entire text file. As for substitute, it has to be lowercase, and then you use slash to separate the components. The first component you specify is what you're looking for. So in this case, the caret symbol has a special meaning. It means the beginning of each line. Okay, so you're substituting the beginning of each line with something else. So you use another slash to separate the thing that you're looking for from the thing that you're replacing with. So the second part is just pound with a space, because we want otherwise there's no space between the pound and the int. So that's why the space is nice to have. And then another slash to end the substitution string, the string to replace what you're looking for. And then the G is not necessary here, because the G specifies that if you have multiple occurrences of the same pattern on each line, do substitution for every single occurrence on the same line. But each line only has one begin line, so in this case the G is not necessary. So that's how it's done. So now I have extra pound signs, and U, lowercase u, is undo, so it's pretty easy to do it and undo it. All right. Are there any questions? No questions? Okay, which part do you think is going to be the trickiest part?
Probably flattening it all.
The flattening part?
Yeah, because you have to get that right, or everything else will be messed up.
That is correct, but that's why you want to do the flattening part when it's still in C and C++ form. So that way you're not struggling with both the assembly instructions and addressing modes with the logic of the program itself. You can focus on the logic first, and then later on, once you cannot flatten it anymore, then you can convert it into assembly. Any other comment? No, nothing? Well, I have a completely unrelated question. Since most of you are on the computer science transfer degree track, you must have taken a few math classes, whether you like it or not. So the question is, do you find my math lab useful in your math classes?
Yes.
Yes.
So without that resource, it would kind of change the way the math classes are conducted? Okay. I'm asking only because there is something coming down from the power that be that basically will require everything other than D2L to be authorized before they can be used. So anything that can either collect homework assignments for you to participate in any type of activity for grading purposes, for you to interact with your professors, they all have to be authorized first before they can be used any further.
Do you want us to place that we like using MathLab in writing, so you can submit that as actually something like evidence to them?
They have an academic senate meeting today,
Yeah.
so if you can go to the meeting, that would be somewhat useful. But it's boring for most people, so I'm not sure whether you want to do it or not. But I have already expressed these resources are really useful to our students. What they're trying to do is not really the objective is not to make you guys miserable because we are removing all these resources from you. Well, at least the professors don't want to do that because we actually see you all day long. So, but the people who are making these policies don't. Okay, they are on 1919 Spanos Court. Okay, which is not one of the campuses. Okay, they never really have to meet our students. But their concern has to do with FERPA, which is education record privacy kind of thing. You don't want your grade to be accessible to somebody else. So the district, basically is saying, okay, if a system is not, if we cannot ensure, all of the requirements and standards are met, on the system, we don't want our students to have access to it. In case, the students, student record got stolen, we don't want to be sued. So we don't want to, give, student access to anything that can potentially be a problem. So the three things that they want, the three standards they want on every system, on every platform that you guys use, would be: one is ADA compliance. Okay, can a blind student or a deaf student use the system? FERPA issues. Okay, is it secure? Okay, is your privacy ensured? And then the third thing, which is kind of interesting, it does not apply to a face-to-face class, but it applies to online classes. It's called REC, which stands for Regular Effective Contact. In other words, is the online professor conducting the class in a course by correspondence way, which is basically just giving you all the homework assignments, and here are the tests, and this is the reading material. Have fun, bye. Or is the professor actually interactive? Okay, you're looking at your grade and go like, hey John, I can see that you're having some problem with this homework assignment and you're doing really great with the other ones. Do you have any particular question about these concepts and so on and so forth? So basically having that, quote unquote interaction component, that's REC, regular effective contact, but it applies mostly to online classes, which basically means, for face-to-face classes like this, I can ignore your questions all day long and I won't get into trouble because of that. I can just talk to the ceiling, I'll talk to my book.
Won't get in trouble with the district, might get in trouble with your students.
Exactly, which I don't see. So those are the issues, but the REC part is the difficult part, because if a publisher website does not have an ability to generate a log or a report of how a professor is interacting with students using that system, it's not going to meet that last requirement. ADA compliance is easy, okay? We got tools, okay? We just point the tool to a URL and it can check everything, okay? No problem, no issues. FERPA, kind of not an issue because, we can check the security of a website, scan it, look for potential issues. So for the most part, that is not a big issue. But the last one is a big issue because a lot of publisher websites, like MyMathLab, may not have the mechanism to report, how a professor is using that website to interact with students. Okay. At what time, Professor XYZ send an email to student ABC? Okay. Does it have the ability to generate a log or a report of that stuff? I don't know. Do you guys have any interaction using MyMathLab with your professors?
I know if you get stuck on a problem, you can actually email the professor and
Okay.
it'll send them everything that you've worked on for that problem,
Okay.
any hints you've used, all your answers so far, and ask for help on that specific problem.
Now, is it done through just MyMathLab, or is it actually getting outside to your regular email accounts?
It sends it from MyMathLab,
Okay.
but I don't think it has any way of tracking responses.
Okay. But does your professor log into MyMathLab to view the actual message? Because if it's a math equation or a plot of some kind, I'm just kind of thinking, I have never used MyMathLab, so I'm kind of imagining that when you're stuck with a problem, MyMathLab has a snapshot of that particular problem. So when your professor logs in, they can go back to that snapshot and go, okay, I can see where you're at. The next step is going to be this and that.
I think that it doesn't log it. It doesn't make you log into MyMathLab, but it gives you a screenshot of it, and
Oh, okay.
I think it'll be recorded in the system somewhere.
Okay. Go ahead.
Because MathLab is like the account is usually from like a professor has an administrator account,
Uh-huh.
and he would usually like when we like he has a code for us,
Mhm.
and when we actually get into the course, we use the code to get into the MathLab. So yeah, he probably like has an entire list of us.
Okay. Now, do you use your own password as the same password here, or does it? So it's a completely different authentication
Completely
system.
different account.
Okay. Do your professors set up the accounts for you guys, or do you have
He
to set
said
it up
that-
for yourselves?
He says that the main account, I think.
Right.
But then he gives you a code, and you can use the code to get into
Got
the
it.
class.
So you have to set up your own account
Yeah.
first, and then you use the code to basically quote unquote enroll yourself into one of the classes that is hosted by MyMap.
Yeah.
Okay, gotcha. You had a. Yep.
Well, mine was just on Moodle. Is that safe? Or are we gonna lose it?
It is safe as long as I'm not doing any grading, right?
Oh, okay. So that's the criteria.
That's why I'm not grading
Uh,
yet. Because I want to keep your education record safe.
So it's got the A's.
It's still non-existent. It cannot be stolen.
So we're not failing yet.
Well, actually, I did grade Subtractor last night, and I found some people to be quite smart, because with the Subtractor, half Subtractor, there are two gates. There are two AND gates that are configured exactly the same way, and a few of you realize and say, "Hey, it's the same thing." So instead of having three AND gates, some of you optimized it to two AND gates and tap one of the output of one of the NAND gates to also serve as the borrow bit. And I just thought, wow, that is pretty good. I did not even realize, in class that there are two AND gates that are identical and can be optimized into one single AND gate.
We're just so intuitively smart.
Yes.
We're all a bunch of savants.
Well, by this time, it's.
You snicker.
All right. So getting back to the homework assignment, are you guys feeling more comfortable now? How to proceed? Because it's due on Tuesday, so we gotta get on it. I don't think it's gonna take too long. Once you get used to the steps of how to do it. So I would definitely either review what I did today, because I only spent about 45 minutes or so on this particular problem. So it really is the approach. If you approach this problem in a different way, like look at the C code, understand the C code, and then try to translate it directly into assembly code without the intermediate steps, that would be much harder. Okay, because now in your head you have to track the use of the registers, the logic that you're translating, and also how deep it is nested and stuff like that, all at the same time. And that makes it very difficult. But if you use the flattening approach, you can flatten only one part of the program in each step. Test it again, and then flatten some more. So that makes it easier to debug, because if there's one step that you made a mistake in, no problem, okay? You just kind of backtrack and say, okay, let's start from before this step again, okay? Or look into what I just did and try to figure out why it is not working. Okay, so the worst thing that someone can possibly do with a homework like this is really just to dive into the assembly code and try to write the entire program in assembly before the first attempt to debug and run it. That would make it very, very difficult. I would not do it myself. Okay.
Could you make any type of graphics or anything of the sort with assembly code, like Java's graphic engine? Like any?
Like a flowchart, something that reflects the control structure.
Well, I read that the guy who wrote Roller Coaster Tycoon wrote it all in assembly language. So I was wondering how.
Oh, so you mean the application, the program itself?
Yeah.
Yes, absolutely. This is kind of interesting because it has to do with the operating system too. With Windows, it may not be as easy, but the way X Windows work, which is what GUI programs run on in Linux, X window is actually a client-server model. So a client program, which is the one that wants to display something on the screen, it is called the client, actually makes a connection, kind of like a socket. It's kind of like a network connection to the X server, okay? And at that point, once the connection is made, it's all file operation. So once we get to file operation, you need to learn how to make sockets. But once you know how to make sockets and deal with file operations, yeah, you can make your GUI program and write it in assembly. It's not going to be easy, but it can be done. Yep. Any other questions? right, if there are no other questions, I'm going to end today's class just a little bit short. I'll be at the lab today, so if you want to kind of work on your homework assignment today at the lab, I'll be there to answer questions and upload the video right